Hi guys, so we are in video 4, chapter 19 now. Again, follow the PowerPoint from the shared class files. Picking up on slide 27. So we already introduced what standard conditions are. If we have all concentrations are 1 molar and all partial pressures of gas are 1 atmosphere, then those are our standard conditions. If it doesn't give us a temperature, we usually assume the temperature is 298 Kelvin, although that can change on a given problem if we need to. But when we have standard conditions, that gives us our thermodynamic values with the not symbols. But we had to address that there are some cases where we do reactions that are under non-standard conditions. So if I want to know delta G, if I run a reaction under normal conditions, which is very different from standard conditions, what would the delta G value be? Okay, so if I just mix together some HCl with some sodium hydroxide, I just want to know what the delta G of that reaction is. I have to know what the concentrations are and be able to plug it in to get the values I need. So let's calculate. We have an equation. The delta G under non-standard conditions, which most of the time this is the delta G that we need. It does depend on the delta G naught value. So when we work these problems, it's often a 2-part problem where in order to find delta G under non-standard conditions, we have to find delta G under standard conditions first. Then we plug that number in right here in the equation, and then we have our R value is 8.314 joules per mole Kelvin. T is our temperature in Kelvin. Natural log of Q, and this is the Q value that we used in equilibrium, the reaction quotient, which should be for any given reaction is the products over the reactants. So I have a reaction here. Let's see, there it is. 2 NOs reacting with Cl2 to form 2 NOCls. I've changed this reaction because the previous problem that was in the PowerPoint, some of the values weren't in the appendix that we needed. So I changed the reaction, and actually one of the boxes that's going to pop up in a minute is the wrong one. I'll talk about that in a second. But in order to solve this problem, I'm going to have to first find delta G naught, because this one actually walks me through. Find the delta G value under standard conditions. So all I do for the reaction I have, I look up in the appendix the product value, look up that delta G, multiply by 2, that number is going to go here, minus the delta G of this one times 2, plus the delta G of that one, sum those up, that's going to go here, it's going to give me the delta G of the reaction. That's under standard conditions. That value will come down and be plugged in right here for the second part of the problem. What's the delta G value when I have the NO pressure is 0.1 atmospheres, the Cl2 is 0.3 atmospheres, NOCl is 2 atmospheres. So if I write out my Q value, this is what's messed up on our table. The Q ought to be the pressure of the NOCl squared. So that's going to be 2 atmospheres on top squared, so that part's still fine, over, and now we're going to have 2 things down in the bottom. It's going to be NO squared times Cl2. So in the bottom, forget what it has here. It's going to be the 0.1 atmospheres for the NO squared times the Cl2 is going to be 0.3 atmosphere. So it'll be 2 squared over 1 squared times 0.3. That's going to give me a Q value. It's going to be different from this one. I'm going to have to come back later and fix this, but for you guys, just go by what I said. Once I get the value of Q, I can plug that number in right here. And now I know delta G naught from above. I just found what Q is, plug in my R and my T for 298 Kelvin, and I can solve for delta G. All right, so just keep moving. What do we do? There are a lot of problems as you work problems in Mastering Chemistry or work the practice test that's in the shared class files. There are going to be several times where they say, what's the delta G of this reaction, or use delta G to find the equilibrium constant, stuff like that. There are going to be various times where we have to realize that at equilibrium, or when a reaction goes from being non-spontaneous to spontaneous, those are the 2 cases where we plug in a delta G value of 0. Okay, so if the delta G under whatever conditions we have. If the reaction's at equilibrium, chances are the pressures and concentrations are not all going to be 1 atmosphere and 1 molar. So most of the time when we're at equilibrium, we are not at standard conditions. So at equilibrium, the delta G value equals 0, but that's the non-standard delta G, not the standard delta G. So what I mean is, this delta G value is the one that gets plugged in as a 0. Delta G naught is calculated from the appendix. So if I plug in a 0 here, and then if at 0, that's the point where it's switching which way the reaction is going to go. If it's at 0, it means that the reaction doesn't want to go either way, which means it must be balanced, which means that we are at equilibrium. So if we are at equilibrium, there's two things that are important. I just said the delta G is 0 at equilibrium, and my Q, if I'm at equilibrium, it becomes K. So I can kind of adjust my equation. If I plug in a 0 here, switch Q to K, and then I just subtract this part all over, it gives me another equation that's very useful. Okay? This is the same equation as that one, it's just under a specific set of conditions. This equation helps us correlate if we know delta G naught for a reaction, the standard delta G value. It's very easy to connect that with an equilibrium constant. For any given reaction, if you know the equilibrium constant, you can find delta G naught, or if you know the delta G naught, you can find the equilibrium constant. So that's a nice little equation you should know to relate those two values. The next slide has an example. So I have a reaction. It's the auto-ionization of water. So this is the reaction we wrote in chapter 16, H2O plus H2O. One water gives a hydrogen to the other water to form H3O plus and OH minus. So that's the reaction it's talking about, the auto-ionization of water. And it gives me the standard free energy change. You need to know that if it says the standard free energy change, that means it's delta G naught. They're giving you delta G naught is 79.9 kilojoules at 298 Kelvin. From that information, we should be able to find the KW value, which is the equilibrium constant for that reaction. How do we do it? Well, we use the equation we just introduced. So look at your numbers. If I go back, I'm going to plug in the 79.9 kilojoules for my delta G naught. R is 8.314 joules per mole Kelvin, but if I plug in those numbers, I'm already screwed up. I can't plug one in as joules and the other one in as kilojoules. So I would put them both in kilojoules, 79.9 for delta G and 0.008314 for R. Doesn't matter as long as they agree. The temperature it said on the previous slide was 298 Kelvin. And if I plug all that in, you should be able to solve for K. Now, to do that, you're going to divide the negative RT over, and then to get rid of the natural log, the second function on your calculator ought to be e to the x. So you're going to divide these over, get a number on this side, just do the 79.9 divided by the 0.008314 times 298. Get that answer, don't forget the negative, and then do e to that number, that'll be K. We already know what the value of K should be because we've learned KW is 1 times 10 to the minus 14. So you should get very close to that number when you solve this problem. Another one, similar idea, one more step. Calculate the equilibrium constant Kb for this reaction. Again, it's a reaction we know, ammonia plus water yields NH4 plus OH, so this is just a normal base reaction for ammonia. Calculate the equilibrium constant using the standard free energy formation. So the difference between this problem and the last one is this time I didn't give you delta G naught. You have to figure that out yourself. How would you find delta G naught? Well, I hope that you realize you just look in your appendix, do the product values minus the reactant values, that'll give you delta G naught. Then plug it into the equation, delta G naught equals negative RT ln of K. Plug in your R and T values, solve for K, and we know if you look up the Kb value for ammonia, it should be right around 1.8 times 10 to the minus 5. So there's your answer down there that you should get to somewhere close to that. And that's the end of chapter 19.